The next one.
Because it's a delicacy.
Yeah, me too.
So is this Seal's raw eyeball?
Oh,
Podcast.
yes,
Seal's raw eyeball is a delicacy.
that's obviously a delicacy.
They are beautiful.
Let us get started and not talk about seal's eyeballs or snake's hearts. Yeah, not those things. We're going to talk about the sun and what makes the sun shine. So we've learned the song, the sun is a mass, incandescent gas, gigantic nuclear furnace, where hydrogen is built into helium. That's what we're going to focus on today. Hydrogen built into helium. So this here is actually showing what we understand as the sequence of reactions that releases energy in the sun. So we call this fusion, two things coming together. And notice that we have a key here so we know what things are. Neutrons are blue, protons are red. Hydrogen nucleus has one proton. Hydrogen 2, because it's still hydrogen, it's still one proton, but it has two things in the nucleus, so it has one neutron. Hydrogen 2 is also called deuterium. Hydrogen 3, not shown here. Helium 3, I thought I had hydrogen 3, but no. Hydrogen 3 is called tritium, by the way. Helium 3 has no special name, two protons and a neutron. Because it's helium, it has two protons. Hydrogen 3, how many protons would it have? One, and two neutrons then. And helium 4, this is your standard helium here. So the reaction whereby the sun produces all of the energy, we need its light, we need its heat, we need its energy, right? Is this reaction. So it starts with two hydrogen, two protons coming together. Remember, those protons are repelling each other because they both have a positive charge. So they have to be coming at each other very rapidly to have enough energy to overcome their repulsion and actually collide. And if they do, something really weird happens. One of the protons disappears and is replaced by a neutron. Now, when I was in high school, I thought this made perfect sense, that essentially a neutron is a proton with an electron on it. But that's not true. If you look at the picture of that back there behind Eli, it shows us what protons or neutrons are made of. That atom in the center of that diagram is a helium atom. So it has two protons and two neutrons. But when you look at it, you see there's four things, but each of those four things is made up of three things. There is what we call quarks. Quark is a nonsense word from James Joyce's Finnegan's Wake. And Murray Gell-Mann proposed that we call these subatomic particles that make up protons and neutrons quarks. And the two lowest energy quarks over on the left in that chart there behind Eli, you have the quarks. It's the right part of the left. You see it split into two parts, the right part of the left. You have the quarks, and the two lowest energy quarks are up and down. And all protons and neutrons are made of up and down quarks. The proton is an up, up, down. The neutron is an up, down, down. And so what's actually going on here is that an up is annihilated and a down is created. And in the process, it creates this particle that's a positron and an electron neutrino. It's pretty complicated physics, particle physics. So, do you need to know particle physics? No, you don't. What you do need to know is that through the magic of particle physics, a proton is destroyed, and in its place is created a neutron, a little tiny neutrino, and a positron, which is a positively charged version of an electron. It's the antiparticle to an electron, if you want to be all technical like. Because it's the antiparticle to an electron, it's going to pretty quickly meet an electron, and then the two annihilate, and all of the energy of this electron is turned into photons. So this gives off a fair amount of energy while creating a hydrogen 2 from 2 protons. 2 hydrogen, 1 makes 1, hydrogen 2, and energy. Then a hydrogen 2 meets another hydrogen. So once again, you've got a positive nucleus. The positive nucleus takes a lot of energy to make them come together. And they collide, and this is just giving off a photon and making helium-3. And you might say, hey, we're at helium-3. We are done, right? No. Helium-4 is the end of this sequence. So helium-3 meets another helium-3. So this here is showing exactly the same sequence as was shown over here. And those two helium-3s collide, and they make a helium-4 and give off 2 protons. Now, if you do the math, how many things came into this? I'm just going to change to the green pen and circle each hydrogen. 1, 2, 3. Oops. And 1, 2, 3. She had 3 hydrogen on one side, 3 hydrogen on the other, a total of 6 hydrogen. Produced 2 and now I'm going to change color for the output products, change to purple. It produced 2 hydrogens, and I should have put a subscript of. This has superscript. Yeah, all hydrogens have a subscript of 1. Superscript is correct. It creates 2 hydrogens, 1 helium, and then it created 2 positrons and 2 electron neutrinos. That's supposed to be a nu. And 2 photons. So that would be the entire reaction. What we really focus on is, first of all, 6 hydrogens to start with, 2 hydrogens in the end. We usually just take away these 2 hydrogens and change this number to 4. That's a net reaction. You have to have 6 to make it happen, but the net reaction is 4 hydrogens produce all of this. And then we take all of this, and we call that energy. Energy because this annihilation event with another electron is going to release energy. And the neutrino is so tiny that we don't even worry about it for the most part. It was only predicted because scientists found very slight violations of conservation of energy, conservation of mass. Very slight. And then, of course, the photon is pure energy. So we just call that energy, so it creates a helium-4 plus energy. Now here's something to ponder. How is this going to create energy anyhow? In the end, the reaction can't continue unless it's releasing more energy than you put in. Right? It's just going to stop if it absorbs energy. So it must be releasing more energy than you put in. And how could this possibly release more energy? And I'll give you the answer because you're actually not a physics class, except for you 3. The reason it can occur is because the helium-4 is a much lower energy state configuration than the 4 original hydrogens. So it's gone to a more stable configuration, just like if you were to think about it, if I started with 4 rocks at the top of a hill and I let them all roll down to the bottom and they collide together and just form a little pile at the bottom. There's lower energy having those rocks at the bottom of the hill together than there was having them at the top of the hill. It's the same idea. Then there's the funkiness of how is that possible? And this is where things really get interesting, I think. You guys have heard of Albert Einstein, and you probably heard of his most famous equation, yes, the one that was just quoted for us by Alwan. Technically, it should be E subscript 0. Has everyone seen this equation? Who knows what it means? Got it?
Isn't C like the speed of light and then M is mass?
Mm-hmm. Mass times speed of light squared is energy. And what this means is that mass is merely a form of energy, which is pretty mind-blowing. Mass is just a form of energy that can be converted into other kinds of energy. What kinds of energy did we talk about in this class? Potential energy, configurational, and kinetic energy, energy in motion. Mass itself is another kind of energy. We call it rest energy. That's what the E sub 0 means. It means the rest energy is mass times speed of light squared. So the actual energy that was released in this whole process came from mass. So the mass of what we're left with is lower than the mass that we started with. And the difference in mass is the energy that was released. So that E equals mc squared will tell us how much energy we're releasing. Every fusion reaction is going to result in a lower energy, or lower mass, in the products than you had, or in the, not the product, that is the product. A lower mass in the products than you started with your original items. Now let me go to slide number 1 in the presentation. This picture actually comes up again. So there we have the difference in mass is what is converted to energy. So that E equals mc squared. And once again, like I said, to be technically correct, that should be an E sub 0. Is mass times speed of light squared. C is speed of light, 299792458 meters per second. That's what C is. And M here is going to be the difference in mass. The mass of helium-4 minus 4 times the mass of hydrogen-1. That's what that M is. Put it backward. That'd be a negative value. There we go. So that's what the mass is. And the energy, it's in units of joules. A kilogram times a meter squared per second squared is a joule. All of this said, what's happening to the mass of the sun over time? It's losing a little bit of mass. If I lose mass, I say I'm lighter. Of course, that requires us to have the Earth here for the gravitational pull. So it really wouldn't be a valid thing to say the sun is getting lighter. But the meaning that you take from that would be correct. The sun is losing mass over time. There's less sun there. If there's less mass in the sun, what is that going to do to the Earth's orbit around the sun?
Less gravitational.
Less gravitational pull. Well, here's the thing. The percentage mass loss for the sun is very, very, very low. So it's really not making any observable difference to us, but it is losing mass.
Do you think it's that why the universe is expanding?
No, I don't.
Because they're losing gravitation.
That's an interesting idea, but no, I don't think so. This graph here is a graph that to the physicist explains how fusion can occur beneficially, how fission can occur beneficially. We have nuclear bombs. The first nuclear bombs made were fission bombs. Was it Fat Man and Little Boy? Is that the name of the two bombs? They were fission bombs. And fission occurs when you have something big like uranium or plutonium that breaks into two smaller pieces. So an example here would be if you start with uranium and it breaks into, let's say, one of these and one of these. This graph has on its vertical axis the binding energy per nucleon, which should mean nothing to you. I mean, I'm hoping it means nothing to you, otherwise you've done way too much preparation. The binding energy per nucleon is telling you how stable the nucleus is, or how low the energy is in the nucleus. So the higher the binding energy per nucleon, the more stable the nucleus is, the lower the energy in the nucleus. Which means that you're going to release energy if you go toward a higher binding energy per nucleon. So you see that going from uranium to lanthanum and bromine is going to a higher binding energy per nucleon, hence it's a more stable nucleus and you're releasing energy. But that's going to stop. The highest binding energy per nucleon occurs here with iron. So you can only split things into smaller pieces and have energy released going from something that's bigger than iron down to something that's closer to iron. And if you get smaller than iron, you see that it drops off pretty quickly. So fission can only occur with things bigger than iron. So things bigger than iron that have unstable nuclei we can call fissile. The things that can be broken into smaller masses and release energy. That's what the first two nuclear bombs were. Well, if you look at the graph, you know, the energy that can be released is proportional to the difference in the binding energy per nucleon. And there's a whole lot bigger difference on the left side than there is on the right side. Which means there's a whole lot more energy that you can release through fusion than through fission. But fusion needs to go up, of course. So for fusion, you have to start with something small and build toward iron. So things smaller than iron can release energy by fusion if they move toward iron. And of course, what has the lowest binding energy per nucleon? It's not shown on this table because there is no binding if you have a proton. But a proton is by itself. It's not bound to anything else in the nucleus. So it has no defined binding energy per nucleon. You can put a number of 0 on it, but it doesn't have meaning because you're not binding anything. And so if you can go from hydrogen down here at 0 to helium up here above 7, that's easily the biggest jump that you can make in this graph. Now you could go from hydrogen over to iron or hydrogen to oxygen, really big jumps there, but that takes a lot more. I told you there's a more efficient process than the one that I just showed you that occurs if you have a nucleus that's over about 16 million kelvins in its core. And the sun's only about 15 million kelvins, so it's just under. And that involves what's called the CNO cycle, where you have a hydrogen added to carbon, then you keep adding, you make nitrogen, then you make oxygen, and then the hydrogen takes off from that. And so the end result is you're going basically from here to there, and that's why it's giving away more energy. So the CNO cycle is a little more efficient. But fusion, small things into big. And notice it has that ending point of iron. That's actually really important. Stars can they can produce energy by fusing hydrogen to helium. They can also produce energy by fusing helium. Now, one of the weird things is there is no stable nucleus that you can produce by adding a hydrogen to a helium. We call that Actually, it's hydrogen to helium. Yeah, I think it's 5 doesn't exist. And so we call that a stopper. So in the whole nucleosynthesis, the understanding we have of how the elements were made, hydrogen could fuse into helium fairly readily. So during the early stages of the universe, it's believed that hydrogen was fused into helium. That's how we ended up with a universe of essentially hydrogen and helium. But you can't add a hydrogen to helium and create something stable, hence it stops there for the most part. Now you can make something with 6 nucleons. So if you have like 2 hydrogen that hit a helium at the same time, or the far less likely a hydrogen 2 hitting a helium, then you can move beyond that stopper. But you get to another stopper at 8. And going past 2 stoppers is considered just impossible. So the early stage of the universe probably only created things that are up to a total mass of, well, up to beryllium probably. And nothing beyond that because of those stoppers. In stars like our sun, all it's ever going to do in its core is fuse hydrogen into helium until it gets to the very end. So the core is going to be building up more and more helium over time because that's the waste product, if you will, of the fusion. And when it runs out of hydrogen, what's going to happen? Okay? There's a couple steps before that that are important to understand, but that is the outcome I'm looking at. So the helium is just being compressed into the core. Helium, of course, is going to take a lot less space than hydrogen because you have 4 times the mass for roughly the same time, size, and volume. And so you're building this core with helium. You start running low on hydrogen and the reaction rate slows down. But remember, the star is being held up because of the outward pressure caused by fusion. If the reaction slows down, gravity starts winning. And the whole core is going to start collapsing. But as the core starts collapsing, you're crushing it and things are going to get hotter. And so the temperature gets hotter until the sun will eventually reach a high enough temperature to fuse helium. And the helium, remember, 8 don't exist. So you can't just fuse 2 helium nuclei together. You have to have 3 helium nuclei all come together at the same time. Which is not a high probability event. It's called the triple alpha process because alpha is what we call the radioactive particle that is a helium nucleus. So the triple alpha process would be the same thing, saying triple helium process. You have 3 helium all come together at virtually the same time, and they will fuse to form carbon. And so our sun will produce carbon after it runs low on helium, and we're in a snap. It'll spend about 10 billion years fusing hydrogen to helium, and I forgot what the time frame is, but it's like a year or so fusing helium. It's very short compared to the time of fusing hydrogen. And so our sun will produce a lot of carbon and some oxygen, and then our sun will be done. Larger stars, when you run out of the helium in the core, you can still fuse carbon, right? Because carbon is not iron. And so it will crush more and create high enough temperatures and pressures in the core to fuse carbon. If you can fuse carbon, you actually fuse carbon with a helium to produce oxygen. And then you combine a helium and an oxygen to produce neon. And then you combine a neon with a helium to produce magnesium and so on. I think magnesium is the next stop, I don't know. But it continues to fuse until you produce iron. So in a very massive star, it will continue fusing very, very short times for the rest of these until you have a core that's basically iron. If you have a core that's iron, you are out of fuel, my friend. You can't release energy by fusing iron. And so then gravity takes over and crushes the thing. And then something really weird happens. I didn't intend to talk about the life cycle of a star today, so I'm going to leave that for later, because we're going to talk about that whole situation later. Right now, I'm only supposed to be talking about the sun. But it's very interesting. So, conditions necessary for fusion. I mentioned this on Wednesday. You have to have high temperature. Why is high temperature absolutely necessary for fusion to occur?
Moving fast enough to glide and fusion them hard enough to be able to use.
Right. You have to have them moving fast enough that they actually will come together. If they're going slow, they'll just come like this, and then they'll repel and move away and never get close enough to stick together. So you have to have high temperature to be going fast enough to actually hit. High pressure is also vital. Just a high temperature gas isn't going to fuse. It has to also be high pressure. Why would you need high pressure? How'd you do that?
I don't know. I think they said to push them together.
The push together is the speed. The pressure is just for the probability of them actually colliding. If you only had two molecules, you'd have a low pressure. And the chance of those two hitting would be very small. But if you have billions upon billions, all contained in this small area, it's going to be a high pressure, and you have a much higher chance of them hitting each other. And I said billions upon billions. Obviously, it's much more than billions upon billions. It's very large numbers. So you need both high pressure and high temperature to have fusion. So that was focusing on the temperature there. Here, we obviously won't go through this a second time. We've already gone through this. Which of these equations is the important one to tell us about the energy released in fusion? All of these equations are correct physics equations involving energy. So I'm not asking you which one's correct. They're all correct. Which one is the important one for fusion calculations? I.e., which one did we talk about already today?
C.
Okay, E equals mc squared. That's the equation we used to calculate mass disappeared, it was converted into energy. This equation up here is the kinetic energy equation. This one here is gravitational potential energy. This one here is relativistic kinetic energy again. So they're all correct equations. But the rest energy equation is the important one for us. I think I have a second question here. Nope. Now this, okay, you guys by now have picked up that I really love physics, right? There's so many things that are so interesting that we talk about. And this one here is really cool. So we have like Hans Bethe. He got a Nobel Prize for explaining what's going on in the sun to make it give off energy. That is hydrogen fusion. But in that hydrogen fusion reaction, remember the reaction, the stuff that I had in energy had those neutrinos. Little tiny particles that carry off a small amount of energy and momentum. They're called neutrinos because, well, they didn't observe them initially. They said, why don't we observe these things? They said, well, they must be small or else we would be able to find them. So the eno is just a diminutive suffix, meaning it's tiny. And they must not have mass, or excuse me, not have mass. They must not have charge because charged particles are very easy to detect. So they must be neutral, hence neutral and tiny neutrino. And so they were predicting, people started looking for them. And eventually they found them. But here's the thing. Neutrinos basically don't interact with us. Right now, neutrinos are flooding through your body. Just going through you. Doesn't hurt you because it doesn't interact with you. It just goes through. Neutrinos go through the earth. They just go through. So detecting neutrinos is really tough. But scientists came up with ways. And one way is to take a chamber and fill it with water. Now, there's different fluids they might use. Dry cleaning solution is one of them. But basically, the first neutrino detector they took a big old underground mine, they flooded it with water and put photo detectors all around it. And those photo detectors are looking for energy released in the very rare instance where a neutrino is absorbed and gives off, well, it undergoes a particle reaction and gives off visible light. Very rare event, something like 1 in every 10 to the 16th or something like that. And so they see a little blip here, a little blip there, and they measure the neutrinos. And so they measured how many neutrinos were going through this tank of water per day, basically. And based on the luminosity of the sun, that is based on how much energy is coming out of the sun every second, they calculated how many neutrinos should be flooding through this chamber of water this distance away from the sun. And then they took the efficiency of their whole process of measuring the neutrinos, and they calculated, remember, the whole scientific method. Your hypothesis has to make predictions that are testable. And so it made a prediction that they should have this many neutrinos per second going through here, and this percentage should be observed, so they should measure this amount. And what did they measure? It wasn't this amount. It was 1/3 of the predicted amount. So now if you're a scientist, you have a hypothesis, it gives you a prediction, you do the experiment, and you fail. What do you do then? You what?
Revise your hypothesis.
You revise the hypothesis. So scientists are very disappointed. As they go back to the drawing board, they're like, where were we wrong? Where were we wrong? The answer to where they were wrong was answered in the 1990s. It's a pretty recent discovery. Once again, if you look back at that table above Eli, it has information about neutrinos. The neutrino, you have 3 flavors of neutrinos. This one here is labeled the electron neutrino, it's now labeled the lightest neutrino. When I was in college, it was labeled the electron neutrino. This one here, when I was in college, was labeled the mu neutrino, and this one was labeled the tau neutrino. They now have different labels. They have different labels, one's the light, the medium, and the heavy, because that experiment done in Japan at their Superconductor Kande facility, they were able to determine that neutrinos have a mass. Remember, we had ENO for diminutive, neut for neutral. There was, when I was taking this class in college, I was taught it may have mass, it may not have mass. If it has no mass, then there is a real problem with the hypothesis that they were testing here. If it has a mass, then the theory allows for the neutrinos to change flavor, to change from being one type to another type. And so as the neutrino comes from the sun, it's going to be changing between the 3 types of neutrino. The sun is only producing one kind of neutrino. The electron neutrino, as I learned, is the lightweight neutrino. But by the time it gets here, you're going to have a mixture that statistically should be 1/3 the electron neutrino or the light neutrino. You can tell my age, right? 1/3 the light neutrino, 1/3 the middle neutrino, 1/3 the heavy neutrino. But their detector was only detecting the one they expected, the light neutrino. So all of a sudden, after this experiment done in Japan, they say, whoa, there should be 1/3 as many neutrinos as we had originally predicted because we're only measuring 1/3 of the total. And that's what they had already measured. And so suddenly, as they learn more about the neutrino, their measurement that they thought had potentially disproved the hypothesis now turns out to be correct. And so you go from the heartbreak of what do we do now? We're wrong. We have to adjust our hypothesis to, wow, I didn't expect that. We were actually right. What we didn't understand was the neutrino. So I'm going through this because it's an important part in our understanding for the sun and how it works. And once again, notice that time frame. This is stuff that's happened, not your lifetimes because you guys are all a bunch of youngsters, but it's happened in my professional lifetime since I've been a college teacher, the understanding of the neutrino part of the problem. What's the equation that relates mass and energy?
Oh, just kidding. I was gonna use that.
I have this slide in here so we can do a quick calculation just to understand how much mass the sun is losing per time. So the world's largest power plant, the Three Gorges Dam in China, when it's fully functional, and I don't know if it is by now or not, will produce 22.5 gigawatts when complete. By the way, that is gigawatts. How many people have seen Back to the Future? Okay, at least 2 of you, 3 of you. Great Scott! 1.41 or 1.21? And he says gigawatts. And of course, all scientists are all, what watts? And it turns out they actually admitted, unlike with Star Wars, when they try to make up, the parsec, or actually it's light years. Light years is a unit of distance, and they try to make it time. They, blah blah blah. They admitted no one on the set knew how to pronounce gigawatts, and so they just said, "Do your best." And that's how they ended up with gigawatts. Questions here? No. So, 22.5 gigawatts, 1 watt being 1 joule per second. How much mass is converted into energy if we were to do fusion to produce that same amount of energy? So, we'll just do the calculation real quick. If the energy is 22.5 gigawatts, what is giga? To the 9, it's billion. So that's 22.5 times 10 to the 9 joules per second is equal to the amount of mass per second. So I'll put delta M over delta T for the mass per unit time, multiplied by C squared.
Whenever you're solving for m, does it have to be mass over time?
Yeah, because what we're doing is doing this.
Oh, okay.
Because power is energy over time. Whoops.
Okay.
Power is energy over. I actually had before this a question slide that asked, what is power? Energy per unit time. It's if energy is converted or used. So to calculate the rate of mass that would have to be used for this reaction, we just take that 22.5 times 10 to the 9th joules per second divided by the speed of light. I'll just put 3.000 for friendliness times 10 to the 8th meters per second quantity squared. Well, 3 times 10 to the 8th squared is 9 times 10 to the 16. 22.5 times 10 to the 9th divided by 9 times 10 to the 16th. I can tell you it's a small number, but I'm going to calculate it on not this calculator. 22.5
So do you now have to move over time?
e to the 9th divided by 9e to the 16 equals delta m over delta t equals 2.5 times 10 to the minus 7 kilograms per second. So if we had a fusion reactor, if we had a nuclear fusion reactor here on Earth that we could use for power production to equal the biggest power generating plant on Earth, we would have to use about 1/4 of a millionth of a kilogram, or 1/4 of a thousandth of a gram per second. So how many seconds are in a day? 8,600 and some. Let's just round that to 9,000. Okay, well, I can do that on this calculator. And you should be able to do that. There are 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. And that's 86,000, excuse me, not 8,000. 86,400. If I take that and multiply it by 0.123452625, I would be using 21.6 grams per day. 21.6 grams. This is 10 grams here, so it'd be about twice that mass of hydrogen per day. Not much fuel requirement, right? That's why nuclear fusion is such a big goal. We spend a lot of money on research trying to find ways to make controlled nuclear fusion. We can make nuclear fusion. We have nuclear fusion bombs. Nuclear fusion bombs require sunlight conditions to make the fusion occur. How do you get a sunlight condition? You make a nuclear fission bomb. Nuclear fission bomb gives you a high enough pressure to make fusion occur. Well, that's just not going to work for us in a power plant situation. So scientists have tried 2 different techniques. One is called inertial confinement, where they use laser beams to heat up and pressurize the fuel to make fusion. I've actually 2 or 3 different inertial confinement facilities, one in Japan and 2 at Lawrence Livermore National Laboratory. So I've seen a lot of presentations on that. The other one I have never seen, that's a tokamak. It's a Russian design where you have a toroidal-shaped reactor. That means a donut-shaped reactor. And in that toroidal-shaped reactor, they use magnetic fields to confine a plasma, a charged gas. Remember, the sun is a miasma of incandescent plasma. To confine that plasma to create fusion conditions. The tokamak is considered the best possible idea we have right now for actually getting controlled nuclear fusion to make a nuclear power plant. And maybe I'm telling too much, but my son is really intrigued by this idea of trying to make nuclear fusion for the future of this Earth. If you can come up with a working nuclear fusion power plant, our reliance on oil is minimized. Oil suddenly would be used just for lubricants and for people's water bottles. Right? We wouldn't be using it for energy anymore because it'd be much more efficient and economical to simply use water. You can take, the top inch of water in an ocean, and that's enough energy to supply our needs for 100 years or something like that. You know, just the not the hydrogen, but the deuterium and tritium in that. So we have enough energy that we can push it off to our many great grandchildren before they ever have to start worrying. Now, there is a time when you still have to worry if we were able to do it, but that time is long after civilization would have ended if we don't develop nuclear fusion as the energy source. So that's why people are really into this. If we can control this thing that makes the sun work and makes all the stars shine, that could answer a lot of our problems. We would no longer be dependent on oil for energy. I spoke on this a lot because, well, it is really important to society if we can learn to control this. And it's really important to cosmology because every single star is running on nuclear fusion energy. If you're into Oakley glasses, they have for their slogan, thermonuclear protection. Why thermonuclear protection? Because it's protecting you from sunlight, which is the result of a thermonuclear explosion. that technically ends the material for today. I had slides for the next material because I knew I was going to end early. And so I'm going to start on this material just, so we have a running start. The next chapter is on stars in general. We've talked about the sun here. We spent the first day of the sun just talking about basically what it looks like and learning about the atmosphere, where we have the photosphere, where light comes from, the chromosphere, the region just above the photosphere where we see pretty pink colors from hydrogen gas emission, and then the corona out there. Also, we learned about the granules on the surface of the sun. Now, when I say the surface of the sun, what do I mean? The photosphere, right. You have to be clear. We use the terminology surface of the sun, but it has no surface. So we have those granules. What do the granules tell us about the sun?
Convection.
That it has convection of the surface. That's right. And that's really important. Like, that's going to be on the test somewhere. You also have the sunspots. What are the sunspots? They're magnetic storms where magnetic fields are coming out and going in. Then the next thing we started talking about was what's going on inside. And scientists using helioseismology have determined that you have a radiation zone or radiative zone that's most of the sun, where energy is transported as photons, but it keeps being absorbed and re-emitted, so it takes at least 100,000 years for energy to get through the radiative zone. And then the convective zone quickly gets it out from there. What else did we learn about? Oh yes, the magnetic fields are a huge thing. The solar storms, where the sunspots are, they come in pairs with either north leading south or south leading north. And every time we go through a solar cycle, it flips. The north and south pole of the sun flip. And when the north and south pole of the sun flip, that means the magnetic field lines, instead of going like this, are now going like this. And that's why you have the opposite leading polarity. So we've learned a lot about how the sun works. And now we're going to take our knowledge we have about the sun and we're going to apply it to other stars. Because the sun is just a typical average old star. Well, if you're going to talk about other stars, one of the first things that's really important to understand the other stars is how far away are they? Now, if you're a flat earther, and now I started looking at Alex because of the evil that Eli hath wrought. If you're a flat earther, apparently you believe the sun is closer than we think. Which is, it's silly, but it's what people believe. How do we know the distance to the sun?
We measure the average wavelength.
But how?
The redshift.
Not the redshift. What?
We can time the light.
We time the light is relatively correct, but it's not the light coming from the sun. We send radio waves to the sun that reflect off of the sun. We measure how long it takes for the radio wave, which is electromagnetic radiation, the same type of thing as light. I said you're on the right track. Measure the time it takes for the radio waves to get there and come back, and you can then calculate how far away the sun is. So we have really quite accurate ways to determine the distance to the sun. Now, if we're going to other stars, that's where we go to this. So the first thing to understand is triangulation. If I stand here and I measure the angle between that bookshelf and Eli, and then I move 1, 2, 3, 4, 5 paces, and I measure the angle between that bookshelf and Eli, it's a very different angle. And so I can construct a triangle with the baseline that I've measured, and then with the two angles I measured, and then I can use trigonometry to calculate how far away Eli is. And so we call that triangulation. And that's an important thing for being able to discuss to determine how far away a star is. So for close things, that works real well. For farther things, it's not quite as easy. Remember the small angle approximation if you measure, well, the distance here is the moon, but you have a person on one side of the earth and the other side of the earth. If you know this distance and you measure these angles, you can determine the distance to the moon. Well, we use essentially that same idea for triangulation. Oh, this is the accurate way of measuring the distance to the moon, just like we measure to the sun. But we call it parallax when we're using it for a distant measurement. So parallax starts with the same idea that I did the triangulation with Eli. But what you do is you measure the angle to something when the Earth's on one side of the sun and when it's on the other side of the sun. So you have a baseline that's twice the Earth's separation from the sun. What do we call the Earth's separation from the sun? Astronomical unit. So you have a baseline that's twice the astronomical unit, 2 astronomical units. And then you measure the angle of the apex of that triangle. Except for one little idiosyncrasy. We actually measure the half angle. And so the baseline here is 1 astronomical unit because we're measuring the half angle. And then we define the distance using trigonometry by just making up a new unit. The distance is 1 parsec divided by that parallax angle. If your baseline is from the sun to the earth. So we'll pick up with the parsec next class period. Have a